In the world of autonomous flight, flight controllers and motors mean absolutely nothing if you lose the link. The radio frequency link is the invisible umbilical cord connecting a $50,000 industrial UAV to its ground control station. But the air is not empty. It is heavily congested with corporate Wi-Fi, cellular networks, physical obstacles, and intentional electronic interference. When an enterprise drone triggers a radio failsafe mid-mission, an amateur pilot waits and prays. A professional UAV support engineer opens the telemetry log, analyzes the RSSI, SNR, and noise floor parameters, and instantly understands the exact physics behind the drop. Today, we are breaking down every major drone radio frequency mode, how signals propagate through space, and how to spot RF anomalies in your flight logs. Let's look at the data. Let's start with the industry baselines, 2.4 GHz and 5.8 GHz. These occupy the ISM bands, industrial, scientific, and medical, meaning they are open for public and commercial use worldwide. The 2.4 GHz band is the universal workhorse. It operates on a wavelength of approximately 12 centimeters. Because the wave is relatively long, it possesses decent diffraction capabilities, meaning it can bend around light obstacles, pass through tree leaves, and handle minor structural obstructions. In your telemetry logs, a 2.4 GHz link provides steady mid-range performance. However, its main vulnerability is urban congestion. Every office Wi-Fi router and Bluetooth device floods this spectrum. When a drone approaches an industrial site, the noise floor graph in your log spikes dramatically. This destroys your signal-to-noise ratio, or SNR, causing massive packet loss and triggering unexpected failsafes. To bypass this noise, high-bandwidth communication uses 5.8 GHz. Here, the wavelength drops to just 5 centimeters. This high frequency allows massive data throughput, which is mandatory for streaming high-definition digital video feeds. But the trade-off is brutal. 5.8 GHz requires a strict line of sight, cannot penetrate concrete walls, solid hills, or dense wet forests. If your UAV dips behind a single obstacle, the signal undergoes instant attenuation. In the flight logs, you won't see a gradual signal decay. You will see a vertical drop from a perfect link to absolute zero in less than a single frame. For long-range industrial applications, commercial operators migrate away from Wi-Fi-based protocols to sub-gigahertz frequencies and advanced modulations. This brings us to 915 MHz and protocols like ExpressLRS or Crossfire. The 915 MHz band, using a massive 32 centimeter wavelength, offers incredible penetration and massive range with minimal power consumption. It is the gold standard for pure telemetry routing over 10+ kilometers. But the real game changer is LoRa hardware, which powers modern ExpressLRS links. Instead of transmitting on a rigid, single-frequency, ELRS utilizes chirp spread spectrum, or CSS. It encodes data within continuous frequency chirps, spreading the signal across a wider bandwidth over time. As a UAV support specialist, when you parse an ELRS log, you must look beyond raw RSSI, which measures raw signal power in dBm. You must look at link quality, LQ. Standard systems fail when the signal drops to -90 dBm. A LoRa-based ELRS system can successfully decode digital packets, even when the signal sinks to -115 or -120 dBm, literally extracting data from underneath the noise floor. If the log shows your LQ stays at 100%, the control loop is completely safe, even if the drone is operating miles away behind heavy geographical terrain. Now, let's look at the forensics of signal loss, RF noise versus intentional jamming. When analyzing a post-crash log, a technical support engineer must accurately diagnose the root cause of an incident. Environmental noise from cellular towers or industrial microwave arrays causes a predictable, gradual link degradation. As the aircraft flies closer to the source, the RSSI strength might remain high, but the link quality slowly erodes because the data packets become corrupted by the background interference. Intentional jamming, however, leaves a distinct digital fingerprint. Broad-spectrum jammers overwhelm the drone's receivers by blasting high-power white noise across entire bands. In the telemetry data, this manifests as an instantaneous anomaly. The noise floor parameter jumps to maximum limits, while the valid packet intake drops to 0 within milliseconds. If the aircraft is hit with a GPS spoofing attack, the RF command link to the ground station might remain completely healthy. However, the GPS sensor will suddenly report impossible positional steps, like the drone instantly accelerating to 400 knots. The extended Kalman filter instantly catches this logical paradox, flags an EKF position variance error, and immediately switches the aircraft into an emergency manual or altitude hold mode to prevent a catastrophic flyaway. Mastering radio frequency behavior is what transforms a standard operator into an elite UAV support engineer. You cannot solve a complex RF failure by simply updating software code. You solve it by understanding radio physics, link budgets, and signal propagation. By diagnosing noise floors and packet rates, we ensure industrial drone operations remain bulletproof in the most demanding environments. If you want to master flight data forensics, learn how to diagnose telemetry links using software-defined radio, and see real-world crash logs broken down frame by frame, subscribe to the channel. Drop your technical questions about ELRS and link quality in the comments below. This is BlackBox UAV. Analyze the data, optimize your links, and fly safe.